This video is about probability, maths games, triangle numbers and isomorphism, making connections between different maths topics.
Here are the activities that we'll be doing in this workshop, and it starts at the bottom because that is where we're imagining the young children joining our school learning spiral. And so we're going to play the red-blue game, first of all with 3 red cards and 6 blue cards, and then a bit later on we're going to play the same game with 5 reds and 5 blue cards, and we're going to think about, is there a difference? What is the difference? And why does that happen? We're going to decide whether a game is fair, or is it somehow loaded in favour of one or other of the players. In a casino or betting situation where people actually gamble, it's always loaded so that the casino will make money. So it's not a fair game. It's important, it's useful, it's interesting to figure out, how do we know whether it's a fair game or not a fair game? That's what this afternoon is going to be about. And then we're going to play a different game called Odds and Evens. And we're going to look at the properties of odd and even numbers when we multiply, subtract. And then we're going to look at these sample space diagrams, two-way tables. And that's where we record the different results of what's possible when we carry out the probability experiment or the game. After that, we're going to look at this idea of isomorphism, and if you've not met it before, you'll understand it after this workshop. And triangle numbers, again, if you haven't met triangle numbers before, you're in for a really big surprise. Triangle numbers are just amazing. They crop up all over the place in mathematics, so many of you will have met them before, but you're going to meet them in a new and interesting way today. And finally, this is where it gets a little bit more demanding. We're going to be looking at some abstract thinking, how to make a conjecture and how to prove mathematically this result that we're going to work on. And it's a proof sorting exercise, and that's a very good method that applies to all sorts of other types of proofs and sorting. We'll come to that towards the end of our workshop. So that's then, in a nutshell, is the program for our workshop.
We'll start off with the younger kids, maybe playing some games. Here in this activity, I want us to look at playing the game, as you can see on the display. My colleagues are going to play the game. If in the game, after choosing 2 different cards randomly from the head or from the back, we have 2 camps here, those who go for the same and those who go for the different. The same means we pick 2 same cards, maybe red and red or blue and blue. Then if we pick red and blue, that is different. So Tony and Caroline, these are the 2 camps. Any one of us can join them, decide which camp do you want to fall in. Are you opting for the same or for different?
If you're not quite clear what is going to happen, you will learn, because we're going to first of all show you, and we're going to ask you, as Temba says, to join in. Well, shall I be same and you be different, Caroline?
Yes, you can choose same, I'll choose different. I'm going to put the cards, I've got 3 reds, 6 blues. I'm going to put them in the hat, and I'm going to take out 2 cards from the hat each time. So you're going to see me take them out of the hat. I'm not looking.
Notice that we start off with 3 red and 6 blue, and our interest is to check whether playing this game with such number distribution is fair or is not fair.
And
So
now
what
all
do
you
you
have to do
think?
is decide, are you on Tony's team, which means it's the two colors are going to be the same, or are you on my team, which means that two colors are going to be different? The first time around, they are different.
Keep a record. We'll play this game. Everybody, please join in. Either decide to be a same player, in which case you win if the cards are the same colour, or to be a different player, in which case you win if they're different colours, as they are now.
And I'm now going to put these back into the hat. So every time we select, there are 9 cards for this particular game in the hat, 6 blue, 3 red. I'm not looking.
Different again. Oh my goodness, Caroline, your team has won again.
If you notice, I take them one at a time. I don't take out 2 at the same time. I take out 1 at a time.
Oh, Caroline's won again.
Hey, Team Caroline, let's go. Team difference. Hooray for the differences. Here we go.
Again.
And I'm not looking. And another one. Ooh.
Oh, Caroline, you're doing so much better
You're
than my
doing
team.
very well, Team Different. Tony, Team Different. Team Different, we are doing magnificently. Tell me when to stop. I'll just.
Oh, I think we're going a bit longer. I want to have some more success. My team
Okay.
deserves some success.
Let's
don't
see.
we?
But that's crazy because, oh yeah, no, that there's not. Yeah, there were six blues. Surely we'd see more blues.
Yes,
Let's see.
it is a bit odd, isn't it?
Oh, there you go. Same.
blues
Okay,
again.
Team
Oh,
Same's
good,
got
good,
3.
good.
Coming up, she's
3
coming
to
up.
5.
I hope you decided right at the beginning which team
Way.
you were in. Okay.
Yeah, you have to stick with the same. Once you've decided whether you're same or different for this game, you have to stick with the same every time, either on team same or on team different.
Oh,
But I hope
you've got 6 and I've got 4.
The more games you play, the more interesting it becomes, because that's where you start realizing what is happening.
Okay, we seem to have a win for different, but they're actually quite close. We've got 5 for the same team and 6 for the different team. We're asking you, do you think it's a fair game? Answer yes or no.
and
Remember-
Sammy says it's not a fair game.
Ah,
And
Yes,
so did
yes.
Mokoena say it's not a fair game.
is there an equal chance of drawing cards of the same colour as cards of different colours?
Every comment I've seen so far is that it's not a fair game. Franz had selected different team different. We won. Mokoena says the game will be fair. Oh, we had a few people chose fair. Mokoena and Liza, they were on your team, Tony.
Right, well,
Mary was on team different.
Okay. So we're going to, it will all come clear, you know, light will be thrown on this eventually. But yes, that's the question. Is it a fair game?
That is what we should keep in mind as we progress. Remember, we are still going to play some more games of the similar nature. Here we have 3 red and 6. What happens if we say maybe 5 red, 5 blue? We keep on thinking, is this a fair game or not? Let's move on.
Yes, let's see.
So this is a great game that you can play with even very young children, age 3, age 4 to 7. And the way you do it is you simply play. And you look to see, are they the same and are they different? And we do recommend that you do play it with 3 of one and 6 of another. It doesn't have to be blue and red. It can be all kinds of different things. 3 the same and 6 the same. Keep the score. You can keep the score on the wall and just play the game and see whether the same or different gets more scores.
You can play with any objects you like. We're doing it with cards. That's quite convenient. But if you're playing with very small children, they might play with 3 toys of one sort and 6 toys of another sort. Whatever is around that they're interested in, it doesn't have to be cards. It can be anything really. That is where it's very clear that you've got 2 types of object. that go in the hat. Well, it might be difficult to put big toys in the hat, but you might have a fairly big box and some little toys.
In the back of our minds, remember, we are trying to look at probability problems here, and we're trying to introduce probability. So the issue of sample space and the issue of fairness of games is what we are trying to look at. We will see as we draw towards the other activities or towards the end what happens. Are we sure this is a fair game or it's not a fair game?
But for these little children, it's just free play, as Caroline said. But then when we come on to a little bit older, at first it's just free play, playing for fun. But then after a while, we can begin to introduce this question that we've already been asking today. Is this a fair game? You can talk about it being a probability experiment. We're going to see, by playing this game lots of times and keeping a record tomorrow and next week and every time we play with the class, and see, today it was 6 for the different and 5 for the same, and we played just about enough time for a lesson starter, and then you want to move on with the other things you plan for the lesson, but come back to the game another time. And keep it in mind that we could be treating this as an experiment that we repeat more and more as time goes on, and we see whether these two numbers of times that the same colours come up, the number of times that different colours come up, whether they seem to be the same, or whether equal.
Right, now we are at years 6 and 7. We still want to find out, is this a fair game? And in this instance, we put 5 red cards and 5 blue. Notice that we now have equal numbers of these different cards, 5 red and 5 blue. Is the game fair? Can we see through watching the game? Let's see whether there will be some fairness in playing.
So Caroline and I will play again. And Caroline was showing you that these cards, there really are 5 of each. And she's put on the back whether they're red or blue, with an R for red and a B for blue. And she's numbered them. So she's got R1, R2, R3, R4, which we've just seen. There's R2. We've seen B3 in the hat, and B4 she's just picked up. So all those cards are numbered so that we can see that actually 5 different cards, R1, R2, R3, R4, R5, R5 I mean, and 5 blue cards similarly. Okay, so you can move teams if you want to, but I'm going to be same still, and Caroline's going to be different, and we're going to play the game a few times and see what happens this time. Same. My team won this time.
Whoops, 2. I picked up 2.
Different. Caroline's team. Ooh.
Remember, after picking the 2 cards, we return them back to the basket or the hat, shuffle them, then repeat the same process.
Ooh, another one for my team. Good, good.
And I pick them out one at a time. First one and then the other, not at the same time.
This is level.
Team different. We're catching up.
But it's level, isn't it? This is interesting. Different again.
Is this one now a fair game, Liza? Is that what you're saying, or the last one? Different again, or let's keep tabs? Keep the tally going.
You can let your comments come on the chat on this one.
Ooh, different again.
Well, hey, come on, team different. Vive la différence. Hooray for the difference.
3 more, Caroline. Oh, different again. Oh my goodness.
We're zooming ahead here. This is great. We're definitely doing well. Oh, okay.
Another one for my team.
same.
Good. And the last one, we're going to do 9.
Going to do 9. Oh, I like that. Stop a nice. Oh, here we go. Oh my goodness.
So it's 5 and 4. So it's not really clear from this experiment. We would have to do many more repetitions of this game in order to get an idea as an experimental probability whether it was fair or not. Is there an equal chance of drawing cards of the same colours, cards of different colours? Answer yes or no. And Caroline's now putting some numbers out for the next game. You and I are going to play this game, Tamba.
So I'm going to do the picking out. I'll still do the scoring. But are you going to be odd or even, Temba?
I'll go for even.
Okay, so team even is Temba's team and team odd is Tony's team.
Right. Here we go.
So I'm going to put the 5 cards in the hat, take out the colored ones and put the 5, these 2. Now it's 2, 3, 4, 5, and 6 going in the hat. So everyone decide whether you're team even or team odd. I'm going to take out 2 cards, and the first one is...
You add them up. So 6 and 5 is 11, so it's odd. So my team wins.
And notice that here we're interested in the outcome. Once you pick the first and the second, add the 2 numbers and see whether you get an odd number or even number.
Oh my
People
goodness.
decided. Team odd, you're racing ahead. Oh my goodness. Is this a
I don't
fair
believe
game?
this.
Is this a fair game? Is there an
Shake the hat, Caroline.
Shake the hat. I was shaking the hat. I'm shuffling them every single time.
Now it's your turn. It's a turn of winning, Tony.
Not getting any. Yeah, share, Tony. Share. You know about sharing. Nice.
Oh, that's for Temper. Very good.
Oh my goodness. Here we go again.
Well, I tell you what, Caroline. Let's. So we've got 6 and 1. Well, so we got 7. Let's play another 6 times, shall we? We want to keep our
6
own
more goes.
clock.
6 more goes. Okay.
Yes.
Yeah, that'll be fine.
Oh, team even. Temba.
Good. Well, I'm cheering Temba because I don't like to see him lose. But if he catches up with me, I shall expect to get.
No, it's a game. Whoever wins.
Oh my goodness.
Another
Okay,
one for
here we
me.
go again.
Right.
1, 2, 3. It was that was 2. 1 more and 1 more. Oh my. So that's 3 more to go. Team even. Start crossing your fingers. Do something. Will that
Probably
change the
the more we're
outcome?
playing this game, that's when we realize is the game fair or not fair? Why am
Fair
I
or not
losing?
fair?
Is it fair?
Okay. Is that 6 now? Is that a total of 12? Oh my goodness. Yeah, that's a total of 12.
No, have one more. It has to be odd.
No, we have to have an odd amount.
Well, I think so, because then that can't end up
Oh,
in
this
a
does
draw.
not bode well. Next number had better be odd. Oh, Alan says he has a question, and oh dear. So we have a question, Tony, from Alan. Can we equate the word fair to bias in the experiment, since the number of odd numbers weren't equal to the number of even numbers?
Well, what a good question. What a good question. And lots of people think exactly the way you're thinking, and that is that if you had the same number of each type, that would be fair. And if you have different numbers, there would be a bias. And if you remember how we played with the coloured cards, we had, first of all, 3 red and 6 blue. So they were different. And lots of people think that must make a bias, that must make the game not fair. And then we did 5 of each colour deliberately, because we thought that people would think, oh yes, this one will be fair because there's the same number of each colour. And now here we've got only 2 odd and 3 even. So, well, you might think it was biased. But the interesting thing is, what's going on in my mind is that when we do an experiment only a few times, we can get completely the wrong impression about what the actual probability is if we were to do it thousands of times. We can get completely the wrong impression. Now, doing experimental probability is hugely important because there are some very important investigations, like medical trials, to find out whether a certain treatment works or doesn't work, medical treatment, or whether a drug is good or not, to find out about that. There's no way of doing it but in theory. I mean, the doctors obviously believe that there's good chance anyway. They believe that their new treatment will work. Otherwise, it wouldn't get as far as going to trials. But these trials are just experiments, and they cannot work out an exact probability. So they have to do it by experiments. And now, if they did just, 25 patients, or 25 people, and did this clinical trial, then they wouldn't get a result that was necessarily telling them anything at all, because with such a small sample, these odd things can happen. And I assure you that odd things have been happening while we've been playing this game. Very strange, unexpected things, because we've only had a small number. We had 13 in the one you can still see in front of you. And actually, it should have turned out that even came up more often, but I'm letting you into a secret there. So,
Tony, we've got a couple of comments. Margaret says having equal number or odd, an equal number of odd or even numbers doesn't necessarily mean the game will be fair. And then teacher, please tell me your name, says that she seconds Alan. The probability of even was less due to less even numbers and more odd numbers. Now Rafiwa has been looking at the others. We played game A, which is at the top of that slide. Rafiwa has been looking at game B, C, and D. Rafiwa says that bag B will give more even numbers. And we've got a bunch of comments here. This is really good, Tony. Oh, hi, Happy. Teacher is Happy. So welcome, Happy.
Very interesting comment. I would urge that as we progress from where we started and we're moving to, just observe what is happening in each situation. Like we had red less than the blue, what was the outcome? And now we looked at the red, 5 red and 5 blue. When they are equal, do we expect that the game is fair or not? It's very tempting to rush to conclusions, but if you play such games and let students, play as many times as possible, with time, you might be shocked that without you telling them anything, they'll pick up that the game is fair or the game is not fair through experimenting. And it is our purpose here to, expose these games to students so that they come up with conclusions on their own without us telling them anything.
Yes, and it's going to be something they enjoy, but actually they'll hardly realize that it's a serious lesson on probability because they'll find it so much fun. And it is a good way to learn probability. Now, what we want you to do now is to close your eyes because we're going to think about a way that you might teach children to understand the process of odds and evens and what's different about them and how you what you get when you add two evens or two odds or an odd and even. So I want you to close your eyes and keep them closed, please, until I tell you to open them. Now think of any two odd numbers, whole numbers, odd whole numbers, add them. Is the sum odd or even? Now remember that. Still keep your eyes closed. Think of another two odd numbers. Add them. What's happened this time? Is the sum odd or even? We're going to do this once more. Think of two odd numbers, different ones. Add them up. Is the sum odd or even? Now you can open your eyes. We want you to note on the chat what you notice. Do you notice anything about adding an odd and adding two odd numbers? And if you're not sure, try another couple of odd numbers and add them and see whether the sum is odd or even. And you see, if Caroline adds 3 and 5 there, the two odd numbers that she's had on those cards, you get 8, which is even. What do you notice?
And if you think it might be a really obvious question, it's not too obvious. Think about what your learners would notice and say what they would say.
Haven't got any answers. Oh, maybe we have. Odd plus odd equals even, somebody has said. Shahzabani has said that. Adding two odd numbers results in an even number. Well, you seem pretty convinced about that. Good, well done. And probably the other teachers agree with you, but all we've done is collected a bit of evidence for that. We haven't proved it. To prove it requires some use of algebra to prove that it always happens for every choice. Anyway, close your eyes again. Same thing, don't keep open until I say. Think of any two even numbers, add them, and is the sum odd or even? Now do it with two different even numbers, add them, is the sum odd or even? Now open your eyes and write in the chat what you notice. And if you're not sure, you can think of ones that Caroline has got on the cards. We see 2 and 4 add up to 6, that's even. 4 and 6 add up to 10, that's even. 2 and 6 add up to 8, that's even. What do you notice when you add two even numbers?
We don't have to limit it to single digit numbers, do we, Tony?
Oh no, you can add 100 and 200 and you get 300. So lots of people, Dudley is saying, lots of other people, even plus even gives even. Okay. Again, I'm sure you're convinced that you're right, but we haven't proved it, and I think we'll leave the proof for another day. But it needs some algebra to prove it, that it works whatever the two odds or two evens are. And the last one is adding an odd or an even. Adding an odd with an even. So close your eyes again. Now think of an odd number and an even number. Add them up. Is it odd or even? Think of another two numbers, an odd and an even. Add them up. Is it odd or even? Let's do it once more. Think of two numbers, an odd and an even. Add them up. Is the answer odd or even? Now open your eyes and write on the chat what you notice. Now if I add 3 and 2 from Caroline's cards there, that's 5, that's odd. If I add 3 and 4, it's 7, that's odd. 3 and 6 is 9, that's odd. 5 and 2, 7, that's odd. And it seems as if, well, have you put it on the chat? What do you think's happening when we add an odd and an even? Lots of you are saying the same thing. You get an odd number every time. Well, that's something to bear in mind. We're going to use it later, and I'm sure it's some homework for you to write down the algebra and prove for yourself that this will always happen. We can't test all the millions and more pairs of numbers that we could have worked on.
Right. In this one, we want learners to try and play the game of red cards and blue cards. In this instance, we have exactly 5 red and 5 blue. As teachers, you are trying to find out, are the learners picking up what is happening as they play this game? Is this game a fair game or not a fair game? You know. Remember also the level of the learners we are dealing with, just like we looked at the previous question. When we start thinking of algebra, we are trying to prove ourselves as educators, is this a normal thing which happens with all numbers? But at the level of the learners, it would be good to try and keep at their level and let them play these games repeatedly with small numbers, 7 plus 9, those are odd numbers, add them, you get an even number and so forth. So in this case here, we still want to find out the answer. Is this game a fair game?
And some children will realize that there's a secret winning strategy. In other words, it isn't fair. And they will not tell anybody else because they're winning. If they choose to be different, they're going to win. Okay, and if they play the game often, it won't win every time, but if they play the game often enough, they will, if there are enough rounds in the game, they will end up winning. And some children will realize that, and other children won't. And so before very long, we're going to explain that and lead up to how you explain it, how you explain that this is not a fair game, even though there is the same number of reds and blues. So here is what we've called a sample space diagram, or a two-way table. We use two-way tables for lots of different purposes, and this is, you see it used here for recording the different possibilities, the different things that can happen. And as you saw, Caroline numbered the red cards R1, R2, R3, R4, and R5. And she numbered the blue cards B1, B2, B3, B4, B5. And so what you see on the two-way table there is lots of tiny squares. There are 100 of them, 100 small squares. And well, the first thing we're trying to figure out, we want you to figure out, is what do the red crosses on the diagonal tell you? So put that on the chat. What do the red crosses on the diagonal tell you? We want you to work out what this table means, and some of you will have seen these sorts of tables before and others won't. And we want you to tell us what you think. Where you see R1 and R1 here, you've got a red cross. Where you see R4 and R4, you've got a red cross.
Mohammed says the X's mean that it's not possible to pick those two cards.
Mohammed's telling you the answer there. Why is it not possible? You see, the two cards where there's a cross are the same card twice. See? So
I've only got one R1. I can't pick two R1s. I don't put R1 back in the hat. Once R1's out, it's out. And I can't pick R1 a second time. I've only got those 9 cards now to choose from.
So the squares with the little cells, we call them, with the red crosses, that they've got crosses in them because, as Mohammed says, you can't pick the same card twice. And so Marvelous is saying this, we remove it and pick the second one without replacing, so the second one's going to be different. So there's no result, where the red crosses are, there's no result in those cells, but all the other cells show some result. So if we go on to the next slide, I want you to think about this here. And what you see here is the same sample space diagram. And now I have covered with yellow triangles some of the small squares, some of the cells. The question is, what do those covered cells represent? And how many are there?
Remember, the experiment is to pick two cards, one after the other, and look at the outcome. Is it the same or are they different? Isn't it?
And Mokoena says there are 10 squares under each triangle.
The rest of you think about what Mokoena says, and other people are saying the same thing. And 10 squares under each triangle. And what do they represent? What are they same? Are they the same color, or are they different colors, or are the different triangles that we see, because there are 4 of them, and do they represent different sorts of outcomes? So there are 10, 10, 10, 10, and 10 under each triangle, as you've said. So we want to know, what is the significance of those particular spaces, little cells? What possible outcomes? Yes, but what sort of possible outcomes, Mohammed? They are possible outcomes, but are they the same? Would the same team win if we got one of those outcomes, or would the different team win? So people are now saying it's the same team that will win. Okay.
Probably we can make use of a letter SAM, S to stand for SAM, just to show that the contents under the small box, I mean, under the triangles there, represent the outcome SAM.
Now here's another diagram. Well, it's the same diagram again, but this time I've covered up with the grey squares. I've covered up different cells, and we want to know what those cells that are covered are. What do they represent, and how many are there under each of those squares? And just write the number and what you think they show. I like the way Lisa has said 10 squares, 4, 3, 2, 1, which was not the answer that we're asking for now, but it was the answer to the triangles.
Okay, yes, yes.
Yeah, that's
a
good
observation.
Very good observation, a very good observation there, Liza. Motlokwa has said 25, and Kenzani has said 25.
The squares, the little cells, represent that you've picked 2 colours the same, or are they different?
Would team same or team different have won if we picked B2 and R2?
People are now beginning to say that they think they're not the same now. These grey squares show different. And it shows you that the blue 2 card and the R2 card roundabout there come up. They're obviously different colours. If I go to here, this is the B4 card and the R3 card. And down here, the cards are, again, a red or a blue card. They're not the same colour. So the greys are covered with they cover up where you've got different coloured cards that come up.
If you're wondering why there's the rows and the columns and they have the same cards, you have one which is the card that's picked first, and the other which is the card that is picked second.
Oh yes, you can think of across the top here, these are the cards that are picked out first on that round, and down the side, these are the cards that are picked out second. We've put this two-way table down with S's and D's filled into it, and we ask you to think about what that two-way table shows and what the labels S and D and X show. So CP has said that the X stands for the same card, e.g. R1 and R1, which is impossible. But somebody has said that S stands for same and D stands for different.
Is it a fair game? And how would you know from this sample space diagram, how would you be able to tell if it's the same? What is the total amount of sames and what is the total amount of differences? Does team same have the same probability of winning as team different or getting a point?
You can see very interesting results coming up now. Like we said, if we look at the whole space, the diagonal, which contains the X, 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 and we have all indicated that it shows that we cannot pick the same card twice. Remember, you pick the first card, then the second. So there's no room for picking the same card twice. And that is why we have the diagonal, principal diagonal there with X, X throughout. Meaning from our sample space, those X's are out. And if we look at the whole sample space or the two-way diagram, we have seen before that we had 100 possibilities, but now we are removing all the X's because there is no way one can pick an X, the same card twice. So we remain with a sample space of 90. Very interesting. Remember, there was a time when we had covered the first, if I can say the first quadrant, there were yellow triangles where we're asking what is covered underneath there. And now we can clearly see that those triangles were covering the outcomes, same color, same color, same color. And if we check all the same colors, we realize that we have actually how many? 40, isn't it? Then with the squares containing different outcomes, that is outcomes where we see different colors, we realize that we have 50. 50 plus 40, like Caroline said before, that gives us 90 possibilities. Right. Coming back to our probability now, what is the probability of picking S, that is same cards of the same color? What is the probability of picking cards of the same color? You recall that it should be 40 in this case because there are 40 possible S colors out of altogether 90 possibilities. So the probability of picking same is 40 over 90, which simplifies to 4 over 9. And the probability of picking different will obviously be 50 over 90. And remember, in our games, when we're playing same, when we're tallying there, we saw that at times you find a student is getting more results favoring different or favoring same. But this table, this two-way table clearly shows us that we can come to a conclusion. And in this case, what is the conclusion? Is this game a fair game? I'm sure from your results on the chart there, we can conclude here that this game was not a fair game. We can see the probabilities of the outcomes are not the same. So these are some of the activities, like I said, it was tempting, especially to the younger ones at the beginning, when you see 5 red cards, 5 blue cards, you think because they are the same, the outcome should be a fair game. But this is a clear demonstration where you involve these learners. They will be the ones coming up with this through the experiments. Then at the end, you guiding them, they get to believe that surely in a situation like this, the game can never be fair. We can see that it is those X's which makes, in this particular situation, this fail to be a fair game, because there is no way you can pick a card two times. I mean, one after the other, two times, same card twice.
Okay.
So with this slide, we can conclude that this game was not fair.
Right, so now we're going to look at the other version of the game we played, where we had 3 red and 6 blue. And look at these 2 space diagrams. What is the same and what's different about these 2 diagrams? I mean, the whole diagram. Sort of stand back, look at the 2 different diagrams, the 2 different tables. There's a lot about them that's the same. So put in the chat what you think is the same and what is different. So the one on the left is the red-blue game, and the one on the right is the odd-even game. And in each case, we've got the 2-way table. So look at the tables closely and what's the same and what's different. The diagram is the same, Mabala says. So we've got S's and E's, and well, what matches? What is the same? The whole diagram is the same, but can you pick out what's matched with what corresponds to what the connections are there?
Look carefully, are the letters different? Different and odd is one of, as a comment. There's
they match, don't they? Same and even, different and odd. Okay, and of course the R's and B's are for red and blue, and the O's and E's are for odd and even, as before. But
and the X's are the same.
Now then, what do we notice about the number of outcomes of each type, and whether this makes it a fair game? So how many are coloured yellow there, where it's either the same or even?
And how many odd numbers are there? How many even numbers? How many red cards? How many blue cards?
So I think if you count the rectangles with O and D in are easier to see that you've got 3 rows or 3 columns with 6 in each row. So there's 18 of each, so that makes 36 O's corresponding to 36 D's. Marvelous has said 36 over 72 are even, and 36 over 72 are odd, so that gives us the same probability. So they've got 36 of each type. So 36 over 72 is a half. So the probability of getting odd is a half. The probability of getting even is a half. Probability in the red-blue game is the same colour, is a half. Probability a half, where the S's are, and again the probability is a half where the D's are. So although we've got different numbers of cards of each type, it turns out that these are fair games.
These are isomorphic games, which means, so they're the same and different. Isomorphic means you're looking for connections, you're looking for patterns. When you spot the pattern, like we just did with those 2 tables, you already know how to handle it. And this exists all over the place in mathematics. Connections and patterns is why they are so important, because you already know that if you already know the maths of one, you know the maths of your new discovery when you see that they're the same, that they are isomorphic.
The iso is the word that means same, and it comes into the language where you talk about isobars, as where you've got equal pressure. And morph is a word, they come from the Greek. Morph means to change. So when you get a change in whatever system you're working on mathematically, with whatever you're doing, finding a function or doing something else mathematical, there's a correspondence in the other system. They are, as Caroline has explained, We've got a common mathematical idea and structure. And this is a wonderful, I say it's a lazy man's way of thinking in a way, a lazy person's way of thinking. Because if you're trying to solve a problem or do some work you've got to do, and you can think of something connected which works in exactly the same way, you've done all the work before, so now you don't have to do it again. You say, oh, but this, in which we're talking about the red and blue games, is the same as the odds and even numbers. So we don't need to work it out. We can see that what we've already done applies in this different situation because they're isomorphic. And so that's that. As people go on using and applying mathematics at higher and higher levels, they learn more mathematics, and they can more often apply this as a method. You know, I'm solving. This is a new problem. Oh no, it's not a new problem. It's a problem I've seen before, but it looked different in a different disguise, if you like.
Very interesting patterns we're coming up with here. Right, you can see from the red-blue game sample space, if we look at closely the contents of the small squares within the sample space, on the left diagram, for example, if we're to remove those S and Ds and so forth, and replace that with dots, as you can see on the right-hand side, you can see that the shape or the structure which you obtain from those dots is actually a triangular shape. Can you see that? And this helps us to see the connection between the triangular numbers and the number of possible outcomes. We'll talk shortly of the triangular numbers in the next slide which follows.
So you've got, if you're counting them, you've got 1 plus 2. As you go down on the rows of dots, you've got 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. Okay. And that number is actually what we call a triangle number.
You can see them here really clearly, and this is a great way to show. You can see the shape, and yes, 1 is still a triangle number. It's just a very small triangle, I suppose. 1 is the first number in the triangle number sequence. So you can demonstrate the shapes, as Tony said, first 1, then 2, then 3. The difference between the two numbers is add 2 numbers and you've got 3, add 3 dots, you've got 6. And the other thing is, again, triangle numbers come up all the time in lots of different ways in mathematics. So becoming familiar with triangle numbers, 1, 3, 6, 10, 15, 21. This is a really important activity for your learners to be familiar with, just like they're familiar with the times tables, so that they can recognize the connections and the isomorphism when they encounter them again. To really, they already know a lot about it if they encounter them another time doing something different.
You see the notation here. What I mean is the way we write it down. That's all the word notation means. T1 is the first triangle number. T2 is the second, which is 3. T3 is the third triangle number, which is actually 6. T4 is the fourth triangle number, which is actually 10. T5 is the fifth triangle number, which is 15. Okay, now if we go to what we had on the previous slide, which was, it was 1 plus 2 plus 3 plus 4, that's T8. So if we count along, 15 is T5, 21 is T6, 28 is T7, and 36 was T8. We'd already counted 36, so now you recognize that was a triangle number. Now, I'm going to tell you the story about Clever Carl. So you can imagine this story. It happened, it's a true story, and it happened when Carl was 10 years old. And he was in school, and his teacher obviously thought they'd have a bit of a rest. And so the teacher told the class that they had to add up the numbers 1 plus 2 plus 3 plus 4 up to 100. And I could imagine the teacher thought this would take the children quite a long time, and the teacher could have a bit of a rest while the children were busy. But in about a minute or two, Carl had got the answer, and he was saying, "Please, miss, I've got the answer," or he was saying it in German because he was actually German. And she didn't believe him at first, but then when he told her what answer he got, she was amazed. And when he told her how he'd thought of the answer, she was even more amazed. So what he did was he thought about reversing this sequence, and if he wrote down 199, 98, 97, 96, counting down to 2 and 1, he thought about it, and he thought, well, each time if I add 1 to 100, 2 to 99, 3 to 98, 4 to 97, and so on, every time I'm going to get 101. So the answer must be 100 times 101 divided by 2, because I've added the sequence in twice, and so the number is 5050. Wow. And so he was a very clever clever child, but he is one of the most famous mathematicians the world has ever known. His name was Carl Friedrich Gauss. He lived from 1777 to 1785, and there is a postage stamp, a German postage stamp, and with him as a younger man, and a banknote with him as an older man from the Deutsche Bundesbank. And yes, he discovered and explained and wrote about lots and lots of mathematics. Now this is a good story, really, because you could use it with your learners. And I think one idea that is about how you could use it is you could give the table that I have given you there, but leave a lot of blanks, and just give a general idea and ask them to fill in the blanks and the totals, and then ask them what they notice about it. Then you can tell them the story. Now, what we're trying to do, the AIMSEC and G10 group, what we're trying to do is to encourage you to get the children learning from their own activities. And here we want to find ways in which that we set them thinking. And in order not to give out, just give them the information, we want to ask them what we call key questions. So key questions are questions that guide the learners in their thinking, that help them to think and understand whatever it is we are teaching that day. And if we were teaching how to add up this sequence, then what sort of questions would we ask? What sort of questions would you ask if you were teaching this to your learners? If you think about it, this is what we call an arithmetic series, where the first term is 1, and the common difference is 1. You add 1 each time. And this Carl's method works if you add a sequence like 2, 5, 2 plus 5 plus 8 plus 11 plus 14 plus 17, where you start off at 2, not at 1, and instead of adding 1 each time, you add 3 each time. But if you reverse the sequence and do exactly what Carl did, you can sum that arithmetic sequence and any arithmetic sequence.
Think about the questions that you would ask about this, but always remember to ask key questions. Questions are more important than explanations.
So after you've asked the questions, and after a lot of the children have answered, then you can go on to give your explanation at the end of the lesson and a summary. But at the beginning of the lesson and through to almost the end of the lesson, try to be guiding their learning by asking questions. So we'll leave that with you to think about, because we've got more to do, more exciting things to show you.
Right. I would like to ask all of you to look at that structure we can see on the screen there. What shape or what geometrical shape is represented by the whole structure?
Post what shape you can see that's made up by all those dots.
I
I
think
can
the
see
whole
someone
structure
saying is a square there.
is square, yes.
Uh-huh.
Yeah,
Do you
that's fine.
notice the square is actually made up of two different geometrical
Triangle.
shapes again?
The
What are
triangle.
those shapes? Triangle, very good. Right, if you look closely at those two triangles, are they equal? Are they exactly the same? Are they of the same size? You realize that whatever answer we give, we are guided by the dots which are making up this shape. If we look at the shape below, what color is it? Is it orangish? How many dots are we having there on the triangle below? No, the interesting thing here, you realize that the two triangles, like we've seen, they are different in terms of size, but if you combine them, they form a square. So the first triangle is actually giving us a triangular number, a particular triangular number. And if you look at this triangular number, which you are seeing from the yellow dots, plus the one generated by the blue dots, the two triangular numbers are actually consecutive numbers. There are two consecutive numbers such that each number is actually a term, like the 60th term. If you go back to the triangular numbers, which Tony was talking of, the way they are progressing, here we have the 60th term added to the 70th term. The sum of those two gives us actually a square number. So one can actually say two consecutive numbers, triangular numbers, give us a square number. And in this particular example, we have a square number, which is 49, which is a result of multiplying 7 by 7. Do you think that the sum of the two consecutive triangle numbers is always a square, judging from this picture here? Can we conclude that the sum of the two consecutive triangular numbers is always a square? Just ponder about that.
It needs proving. It looks as if it probably were.
Yeah, it would be interesting for us to think critically about that. We meet triangular numbers again.
And whatever you answer, you've got to think why that would happen. Now, this looks similar, but it isn't quite the same. Those of you who are really observant and you can remember the last picture will see that this is a bit different. We had not just the colours, but there's something very different about it. And there are two identical triangle numbers here, and they make a rectangle. And this is a bit reminiscent. It's a bit like Carl's method, isn't it? Because here we have got T5, 1 plus 2 plus 3 plus 4 plus 5. And we've got it in green and purple, but it's T5 twice. And therefore, our rectangle is 5 times 6, which is 30 altogether, and T5 is 15. We saw that earlier. And similarly, this is Carl's calculation, twice T100, and that gives us T100 is 5,050. If you look at that for T7, you'll see that exactly the same applies, and now I've written it out in full, you can see Carl's method again, that twice T7, right? You've got 7/8, and that gives you 56. So you get 56 divided by 2. And if you look here, I've just put it there just to remind you of what we had before, where we had a square, and they were different triangle numbers. If we put the same triangle number in this similar positions next to each other with one way up and the other way up, we get a square when they are consecutive triangle numbers and a rectangle when they are the same triangle number. And that's something we need to bear in mind and think about, because we're going to come to this proof sorting exercise. Now, proof sorting is something which is a method that you can use in lots of different ways, but you can ask your learners to sorting into an order, and they've got to think logically in order to get this right. And here what you see is a proof of an amazing result. So this is the amazing result. If one of these games is going to be fair, then the number of objects of one type and the other type have got to be two consecutive triangle numbers. And if they are, it'll be a fair game. So 3 and 6 was 3 red and 6 blue, or 3 odds and 6 evens, and 3 and 6 are two consecutive triangle numbers, and that gave us a fair game. And it always happens. And what you see in this jumble here, which is waiting to be sorted out, is a proof of that result. I just wanted us to think about this as a method in general. This is proof sorting, where we have to think logically and abstractly and rely on algebra. So this proof that we're going to talk about relies quite heavily on some algebra, but it's very simple algebra, but we have to think of each step here and get the steps in the right order. So what we do with this proof sorting method is to jumble up the objects, and in this case it's strips of paper with the different pieces of the argument written on them, and we're asking the learner, it's you this time, to sort them out.
This is a method that you can do. It doesn't have to be a proof. It doesn't have to be including algebra at all. We're going to have an example in a minute. We use the same method. You cut the activity into strips, and then you give it to your learners to sort. You can do this for 4-year-olds. You can do this for 8-year-olds, any age. Just make the activity appropriate. This is a very, very powerful activity. You can watch what they do so you can see what the misconceptions are, and then you can help them with questions to sort the misconceptions out.
And it can be used for proofs in Euclidean geometry, which I know you teach if you're teaching in secondary school. And it's quite hard for the learners to know how to, I mean, they may see which angles are equal or which lengths are equal, but it's quite difficult for them to actually write down the proof in the way it should be written down to be perfectly written. And so doing this with a proof that is correct, but with the proof jumbled up and sorting it out, is a really good way to teach them to do it. Now, I want to tell you how to get hold of, how to find our AIMSEC resources. So the odds and evens games resources are there, and that's the link, and they are on the Aiming High website. But there's many more, there's hundreds and hundreds of different learning packs, and each learning pack contains worksheets which you can print out, templates and instructions for making resources. Then there's notes for teachers, which give you the solutions, curriculum links, suggestions for teaching, and key questions to guide learning. And then there's an inclusion and home learning guide, which gives a starter activity which is suitable for young people of different ages to do together, or whatever your class is if you're teaching in school. And then a collection of learning activities to suit all ages from 4 to 18 plus. So it's designed to provide for teachers in school inclusion. So if you've got people in your class who are struggling, you can give them a simpler activity. If you've got people who are very quick and get everything, understand everything quickly, you can give them a more challenging activity because you want them to make progress. You want them to really meet, live up to their full potential. So it's not a good idea to always ask everybody the same questions, because the ones who are struggling get a sense of, oh dear, I can't do this, and the ones who are really quick thinkers, they get the feeling, oh, this is awfully boring, and I've just got to do a bit more of this. Now, I want to tell you about how you find our resources. So, first of all, as I said, on Aiming High, where there's a list of what you'll find there. And then we've got the app, which you can download onto your phone or laptop, and that will give you all of the resources that you can use offline, so you're not using the internet, save you money. And then we've got our YouTube channel. So you'll find this recording of today's workshop and other G10 workshops on our YouTube channel, and lots more. There are lots of videos there. We're polishing them and improving them and adding new ones all the time. And then there's also the Happy Maths Hour. So every Monday at 5 o'clock the UK time, there is the Happy Maths Hour, where this is not just for teachers, it's for anybody who's interested in mathematics, really. And we just, each time we explore some different ideas in some branch of mathematics or other. So that's the Happy Maths Hour. And now we're coming back to this proof sorting exercise. The last slide you saw this, you saw all of the 10 strips on one page. Now I'm going to show you that we have 2, here's 4 more, and then there's another 4. We're actually going to do this.
It says we have proved that.
Oh, that's not.
It says we have proved.
So can you find the one that says that this is the first one, because we actually tell the people that it's the first one. I think it's A. It's not giving anything away, because it does say, there you go.
It fell on the floor.
We couldn't have got very far without that. Okay.
No.
If you actually managed to print it, or just watch what we're doing. Now we're going to go quite fast through this.
They're all labelled A to whatever the last letter is. We can put in the comments what letter you think should come next if you can see the copy of it. Otherwise, just tell us yes or no. Is B a good strip to follow after A?
We need now, after A, we have to say what it is that we think is true that we're going to try and prove. Okay? So that, when we make a conjecture, we're saying, well, we think this is true.
But Tony, we haven't made a conjecture.
Well, you've got to find it and put it down there. There you go. That if the numbers of reds and the numbers of blues are 2 consecutive triangle numbers, then we will get a fair game. And that's the conjecture. So what do you think we've got to do next? You see the picture on B there is the 2 consecutive triangle numbers that Temba talked about earlier.
So you think this is going to be further down the line then? Should I put this nearer the bottom? I think this is going to come a bit later.
Well, it says we have proved, and we've not started the proof yet.
No, we haven't started, so it can't be that one.
And so
what one could it be? Now that says we have proved. That says adding the equations. Well, we haven't spoken about equations yet. But what about this one? Notation. Label the number of objects as A and B. What about that one? Would that be a good one to go next?
Well, we're going to do some algebra, so we need to know what letters we're going to use and what those letters are going to mean. That's notation, isn't it?
Okay.
So read it again, Caroline.
It says Notation: label the number of objects of the different types as A and B, with A greater than B. The symbol with arrow going both ways means that the logical argument works both ways. The statement and its converse are both true. It's an if and only if argument.
Good. I think we're ready to start proving it now, because what we have got is we have got the conjecture. We don't know whether it's true or not because we haven't proved it, but if you believe me, it is true. But we've got to prove it. We've got the conjecture, we've got the notation. Now we need to start the proof. And usually, or often, I think it's in your hand there, Caroline, when we're going to start the proof, we announce it by saying to prove.
To prove. Okay. So we're going to say what we want to prove. We're going to prove this is a sample space diagram. So we've got what we've been working with earlier, a two-way table. It shows the total numbers of possible outcomes, gray for one outcome, either different or odd, and yellow for the other outcome, for example, same or even. So we're getting somewhere. We've now made our statement, we've made our conjecture, we've established our notation, and we said what we want to prove and how and what tools we're going to use to prove it.
Yes, and what we did was when we were looking at 5 red and 5 blue, when we were looking at the same colour, it wasn't 5 times 5, which is 25. We took away 5, which was because of those X's down the diagonal. Okay. And now we're saying perfectly generally these numbers are A and B, not given as a particular number, but generally A and B. And when we're calculating how many little cells that are in that part of the space diagram, we have to subtract the number on the diagonal for the yellow one.
And remember, if you're watching this and you're not sure about what we're doing, you're still learning something, just like your learners are if they're not sure what you're doing in class. And remember, this technique is a great technique for covering many, many different topics.
But I think the thing about this is that you've got to do it for yourself. Just watching us do it isn't the same. So we hope that you'll treat this as a puzzle, and so then you'll want to sort it out for yourself. You'll want to read what's on these strips, and you'll want to do it and do it for yourself, and not just listen to us. Oh, there we've got another we have proved. So we don't need that one.
Well, we haven't proved anything yet. Okay.
So that goes down to the end or near the end, not actually at the end.
And this says adding the equations. We haven't got any equations yet, so we can't be adding equations we don't have yet.
No, so put that one a little bit lower. And also I see conclusion there. Well, the conclusion's bound to be the very last thing, so I would put that at the very end.
Conclusion's going to go at the end. What about this? No. Is this one go here? Suggestion. This suggests A and B.
This suggests that A and B are consecutive triangle numbers. And the rule generalizing the sequence of triangle numbers is that the difference between, now that's we're not quite got there.
What about for a fair game?
That might be it. For a fair game, the probability of one outcome must equal the probability of the other outcome. So the probability from the diagram there on strip E, the number of yellow, under the yellow shading, is A squared minus A plus B squared minus B. And so that is where you have got them the same color, or I think it was, or was it odd, or yes. And the gray rectangles are where you've got them different colours, and they're AB. And we've got AB plus AB. So there's a little bit of algebra from the sample space diagram. And by rearranging those expressions, we get a squared minus 2ab plus b squared equals a plus b. And then we notice that a squared minus 2ab plus b squared is a minus b all squared. And so, interesting, isn't it? A plus b is the total number of objects that we are playing with. So when we had 3 and 6, we had 9 objects. When we had 5 and 5, we had 10 objects. A plus b is the total number of objects. And that is a square number. So I think it's the we have proved that, the B one next, Caroline. Because we now have proved that it will be a fair game if and only if. So this suggests that comes out.
This suggests comes out. So we think this comes in there.
Yes, but keep that handy because we're going to need it soon.
Yeah.
Now, what we've just proved on this on slide on strip H is that the game will be fair if and only if a minus b squared equals a plus b, and the total number of objects, i.e. a plus b, has to be a square number. So let's call it n squared because it's square. And the difference between the number of objects of the two types, which is a minus b, is n. So a minus b times a minus b is our n squared. A minus b equals n. So that is, what do we know? Equations 1 and 2 are a plus b equals n squared. That's the sum of the objects, the total number of objects. A plus b equals n squared. And the difference between the numbers of one type and the other is n. Okay. So this suggests that they're consecutive triangle numbers because we had those two pictures, didn't we? And in that case, we had where you had two consecutive triangle numbers added together, you made a square number. And when you went from one triangle number to the next one along the line, you added n. So that looks as if they are. So what about the one which refers to equations 1 and 2 now? Because now we've got equations 1 and 2. You had another strip which mentioned, so adding equations 1 and 2, right? What do we get? We get, we might put G and D in the reverse order, but leave them as well. Yes, okay, leave them as they are now, because if we add the one that you've got on the bottom there, Caroline, we have got adding equations 1 and 2. We have got 2a, right? 2a, because b minus b the b's will then not be in the sum when we add equations 1 and 2 together.
Like Clever Carl did.
Is n squared plus n, right? And n squared plus n is a half n times n plus 1. Now, that is the formula for a triangle number if you add them up. Do you remember Carl's number was a half times 100 times 101? Well, yes, because that's how it worked out. So n times n plus 1 gives you the area of your rectangle, as Temba showed you, and then you halve it to get, because you had two triangle numbers, it's the same triangle number repeated in the rectangle. So half n times n plus 1 is the formula for the nth triangle number. And this, so that says this formula gives A as the nth triangular number. And similarly, B is the one before it. And if A and B are, so what we have got is that if A and B are any two consecutive triangle numbers, actually the argument will work both ways. You can try that out for yourself later. Think of it backwards and forwards, and it's the same.
Okay, so that would make sense that these should be reversed.
Yes, so
that statement follows.
Yes, so it suggests that A and B are consecutive triangle numbers, as the rule for generating the sequence of triangles numbers is that the difference between the n and the n minus first triangular number is equal to n, and their sum is equal to the square number n squared. So what have we got left, Caroline? What do we need to now? What have we got left? Are there only those two? Okay, they're in the right order now. We've proved that a necessary and sufficient condition for a game of this sort to be a fair game is that the total number of objects, A plus B, is a square number, and moreover, A and B must be consecutive triangle numbers. Isn't that fantastic? And it's simple algebra, but there's quite complex logical thinking there. And so the conclusion is, for isomorphic games, the proof applies to all games that involve randomly picking two objects from a bag of objects of two different types, where winning or losing corresponds to picking objects of the same or different types, for example, with red corresponding to odd and blue corresponding to even. Those are just examples of this sort of game, but all games of that sort, for the games are fair if and only if the number of objects of each type are consecutive triangle numbers, A and B, so that A plus B equals n squared, and A minus B equals n. So there it is. Here is a list of links, and they are a lot of resources for probability resources that you can use with different classes at different times. They're all on the Aiming High website. There are the links how to find resources on Aiming High. It tells you about our collaborative professional development. And on Aiming High, you've got guides for running your own workshops. So it's goodbye from me until next time.
See you next month. Thank you all so much. This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.